Hi everyone, welcome back to Prakasham Tutorials. In this video, I am going to discuss about sum of two random variables. Let capital X and capital B two independent random variables, and their sum B and their sum is denoted as W. That W is equal X plus Y. So now the probability distribution function of the random variable W is given by if W of W is equal probability of W less than or equal to W. This is the definition of distribution function of the random variable. But here W is the sum of two random variable. Substitute W is equal X plus Y less than or equal to small w. So the distribution or probability is equal integral of the density function, which is equal integral minus infinity to infinity integral minus infinity to infinity joint density function of the random variables x and y into dx dy. So using statistically independent random variables condition, joint density function is equal to product of their individual density function. So that is fxy of x comma y is equal fx of x comma fx of fx of x into fy of y. Applying that condition here, which is equal to RHS term integral minus infinity to infinity integral minus infinity to infinity fx of x into fy of y dx dy. Separately arranging the x terms and y terms on RHS side of this equation, we have integral y is equal minus infinity to infinity fy of y dy. Integral x is equal to minus infinity to but x plus y is equal to w. From this equation, uh, w is equal x is equal to w minus y. So integral minus infinity to w minus y fx of x dx. Similarly, fw of w is equal integral x is equal minus infinity to infinity fx of x dx. Integral w is equal to x plus y. Now we have the y, so y is equal to w minus x. So integral minus infinity to w minus x fy of y dy. Similarly, the probability density function is the probability density is equal to derivative of the distribution function. So dfw of w divided by dw is equal, okay, integral x is equal minus infinity to infinity fxy of x comma y. Y is equal to w minus x. So fxy of x comma w minus x dx. Similarly, fw of w is equal integral y is equal minus infinity to infinity fx of x. X is equal to w minus y comma y dy. If x and y are the independent random variable, fxy of x comma w minus x is fx of x into fy of w minus x. Similarly, fxy of w minus y comma y is equal fx of w minus y into fy of y. Supplying these independent random variable conditions into above expressions, we get fw of w is equal integral x is equal minus infinity to infinity fxy of x comma w minus x dx. Now we are applying the independent random variable condition. This term is fx of x into fy of w minus x dx. So similarly, fw of w is equal, applying the independent random variable condition, integral y is equal minus infinity to infinity fx of w minus y into fy of y dy. So from this equation, RHS term of this equation, and from this equation, RHS term of this equation, we can observe that it can be stated that the density function of sum of statistically independent random variables is a convolution of their individual density function. So that is fw of w is equal fx of x convolution fy of y. And what is the definition of the convolution? F of t convolution h of t is equal integral minus infinity to infinity f of tau into h of t minus tau d tau. That is the convolution between two signals. Similarly, here also in the same concept, the RHS term is convolution between convolution of a individual density function. That is fx of x convolution fy of y. And this is the sum of two random variables. And the same concept can be applied to the more than two random variables. So suppose for example consider three random variables, sum of three random variables. So that is W is equal x plus y plus p. Then the density function of the W is Fw of W is equal to convolution of their individual density functions. That is Fx of x convolution, Fy of y convolution, Fp of p. Similarly, sum of several random variables. The same concept can be applied to the n statistically independent random variables xn. If the sum of capital N random variables is given by y is equal to x1 plus x2 plus x3 and so on xn, then the probability density function of y is equal to the convolution of all the individual density functions. So mathematically, it can be expressed as fy of y is equal fx1 of x1 convolution, fx2 of x2 convolution, and so on convolution, fxn of xn. So this is sum of several random variables and sum of two random variable concept.